we'll pick back up where we left off. We had started talking about motion, and in particular, how do you locate where you are? How do you put a number to that? First, you need to define a reference point. So we talked about maybe my desk in the classroom, and then you could locate anyone or anything in the room with coordinates, as long as you assign a set of units. In that case, it was steps, but probably meters is usually a better unit to use because it's more consistent. But then we talked about a change in position. I was here, now I'm over there. What was my overall change in position? We call that my displacement. So it doesn't really keep up with how I got from A to B. It just keeps up with the fact that I got from A to B. And that's what we're seeing in these examples. It says I walked from my house to the store, but in fact, if I had done a really meandering route, but still ended up at the store, I would still have the same overall displacement, same final minus initial position. So displacement isn't concerned with the details, it's just concerned with the overall effect of the motion. And so that may help answer this last one, which is you walk to the store and then back home. So you start at your house and you end up at your house. What is your final position?
Is it 0 meters?
It is. Yeah, I'm back where I started, and my house is my origin or my reference point, so I am back at 0 meters. What distance have I traveled, though?
2000.
2,000. So I did that trip, and I did the return trip. But what is my displacement?
0.
0.
0. So just according to the math, it's 0. But it makes sense because, in effect, I didn't really do anything. I didn't go anywhere. And that's what displacement cares about. So it is a different thing than distance. I could run around the entire Earth, and if I end up back where I started, my displacement is 0, even if my distance is whatever the circumference of the Earth is, something like 25,000 miles. And then the magnitude of my displacement, pretty easy, it's still 0. The reason I don't need a plus or a minus for 0 is what's the direction of not going anywhere? I don't know. Could be anything. So anyway, some takeaways from that are, one, that the sign of the displacement. So if I look at the sign of it, plus, minus, or 0, what's it telling me?
The direction. You're going east or west?
Yeah. And again, it doesn't tell me about the full details of the motion, whether I went east and then went a little bit west and then back east and west. It tells me about the overall direction that I moved. So for instance, here, overall, I'm now 1,000 meters east of where I started. That doesn't necessarily mean I didn't do some backtracking in between. And before I forget, I'll put, for this last one, not a very interesting displacement. It was 0. I went this way, and then I went right back the other way. But yeah, so positive is an overall motion in the positive direction, which in this example meant east. Negative is an overall motion in the negative direction, or west. And then 0 means no overall change in my position. It doesn't mean I didn't move. That last example, part 3, I moved. I went to the store and back. But overall, it's as if I didn't go anywhere. So, doesn't always mean no motion. Case in point, this example right here. And just by the numbers themselves, we see that distance and displacement are not the same thing. There is a relationship between them, though. So for parts 1 and 2, the displacement and the distance agreed with each other up to a sign, a positive or negative. Meanwhile, for part 3, they are very different numbers. So that may help you see the distinction. What's the difference between displacement and distance?
Distance is how much you've traveled versus displacement is where you end up.
Yes. So what is the relationship between them then? Displacement is the something distance.
Total?
Not quite, because remember, displacement can be 0 when the total distance is 2,000. So it can be a smaller number.
It's the net distance.
Net is a good word for it. I'm going to say it's the shortest distance. It's the easiest trip you could take. That's what displacement is getting at, because the easiest trip I could take to get from my house to my house is to go nowhere, to have 0 displacement. Now, the actual trip might have been 2,000, but displacement is telling me about the shortest trip I could have taken. It is the most direct route. And the last thing, this one may not be obvious, but this is why I was keeping track or giving my displacements names. Displacements are additive, meaning if I break a trip into separate pieces, the displacement for each piece adds up to give the displacement for the total trip. So for instance, I had in part 1 a displacement from my house to the store. In part 2, I had a displacement from the store back to my house. And that should, if, like I'm saying, displacements are additive, be the same as the displacement from my house to my house. And it is because we found that first displacement to be a positive 1,000 meters. The second displacement was negative 1,000. And the third was 0. And that does work out. So I think of this as if I take 2 steps forward and then 1 step forward, that's equivalent to 3 steps forward. I can add those displacements. Also, if I take 2 steps forward and 1 step back, that's equivalent to 1 step forward. So displacements you can break into pieces for different parts of a trip and they will still add up correctly. The last thing is we had that positive or negative and it's telling us the direction. So displacement is a vector quantity. It's something where both the number, which we give the technical term the magnitude, and the direction, in this case it was the sign, matter. Meanwhile, for distance, we only cared about a number, and so we call that a scalar. It's just something that scales up or down. It has no direction to it. All right, so can you think of other examples of, we'll start with scalars. They're a little bit easier to think about.
Speed.
Speed.
Kilograms?
Yep, kilograms, so mass. That's just the amount of something.
Temperature?
Temperature. So it does have a sign. It can be negative or positive, but it's not telling you a direction. It's not telling you east or west. It's just telling you, are you above or below 0 degrees? So yes, it is a scalar. All right, and I'm going to throw in time. That one actually can be argued in modern physics, but anyway, I'll throw in time. And now I'll pivot over to vector quantities. So can you think of things where the direction is important to know?
Acceleration.
Acceleration. So we will find out here pretty soon. Acceleration can mean actually quite a few things. It can mean speeding up, slowing down, or changing direction. And that arrow, the direction of the acceleration, is telling you kind of which one of those is happening. There's something very similar to speed that we'll learn about in here. And you can actually see a hint at it on the next page. But it has a direction.
Velocity.
Yes. So what's going to be the difference is speed is something you read off of your speedometer. It's a single number. Velocity is take that number and combine it with a compass reading, the direction you're going. And the net total of those two things is what we call velocity. That's kind of the easy way to think about it. And I'm going to throw in forces as the last one. Which way you're pushing or pulling is important. And we'll have to do a deep dive on vectors versus scalars in the next chapter, but that's all we need to know about them for now. All right, now we're going to start thinking about not just how or where I move to, but how quickly, the rate at which I'm moving. And so that's where we're going to talk about 4 types of kind of motion quantities. It's going to be average velocity, average speed, and then a little bit later, instantaneous velocity and instantaneous speed. After we get through this section, I'm going to stop saying instantaneous. That's why it's in parentheses, because we will typically stick with these two from then on. But I need to tell you about averages first, because that's how we're going to define the instantaneous values. So, average velocity is just trying to get a sense of overall, how fast are you moving? How quickly are you getting from A to B? So it is displacement divided by time. So we find that displacement between 2 points, divide by the time it took for us to get between those 2 points. And as always, a change or a displacement is final minus initial position. And same for that time span. So this is the time when the object is at that final position X. This is the time when it's at that initial position X0. A lot of times that ends up being 0 because we kind of start the stopwatch when we observe the object to be at X0. But the units will be the units of displacement, which is meters, over the units of time, seconds. So meters per second. And we can sort of plot the motion of something over time, and we'll see that the average velocity is a specific feature of a graph like this. So these graphs can be kind of confusing because the time axis is the horizontal axis, and that forces the position to be the vertical axis. It feels a little bit backwards. So this is t for time in seconds, and then x for position in meters. So if I'm looking at this and I still say the positive direction is east, east is actually this way. It's up on this graph, and west is down. That's the confusing bit. So in a little bit, I'll show you how you could just kind of turn the graph in your head, and it's a little bit easier to think about that way, but we are stuck with this if we're measuring against time. So what would you say this object, it looks like, I guess, some kind of animal, what would you say it's doing in this first graph?
Standing still?
Yeah, because its position is always -2, so 2 meters west of whatever the reference point is. Throughout all of time, you will still find it to be at -2 meters. And the average velocity will tell us the same thing, that on average it is not going anywhere. In particular, it says to find it between 1 and 4 seconds. So that's going to be, where is it at 1 second? That's my t0. And then where is it at 4 seconds? That's my time t. But at both times, it is at -2 meters. So minus, minus. And see, again, that feels kind of backwards that we're putting the later time first, but that will give the correct signs for everything. So if I calculate this, it's -2 plus 2. That's going to come out to 0. So no overall motion. But again, that would be true even if this animal were moving, as long as it comes back to where it started. So it could have a motion like this, maybe. You don't have to draw this one. But as long as it starts and stops at the same position, in effect, it's as if it didn't move. And the average velocity captures that. What is the effective motion? Okay, now we'll do the same over here. So I need to find the average velocity between 1 second and 4 seconds. So this will be my t0 again. This is my time t. I want you to take a second to try and find that average velocity. And just looking at the graph, see if you can predict whether it's going to come out positive or negative and what that means.
Is it 2 meters per second?
It is, but I'm going to be a little bit annoying about it and say you're missing something. It's something you just didn't say, but you got it right. You just didn't say one thing.
It's 2 meters a second east.
Sure, or positive 2 meters per second. So that plus has meaning now. It's not just because it's a number bigger than 0, it actually means to the east. And so we need to report it. Am I going to care about that much moving forward? No, but I just need to point it out now that it has a purpose. So we started at -4 meters. So this animal was 4 meters west of whatever this reference point is. And we ended up at positive 2 meters, 2 meters east of the reference point. And so we still do final minus initial. So it's positive 2 meters minus the initial was -4. We did that between 1 and 4 seconds. And so that is 6/3, or positive 2 meters per second, where this means overall motion to the east. The other thing I'm going to point out is we actually found a very specific feature of this graph. I looked at something between this point and this point. In particular, I had to find the displacement, and that's going to be this difference in coordinates. That's my delta x. And then this difference, my delta t, and I divided them. So what did I actually find about this graph?
The slope.
Yeah, I calculated the rise, delta x, over the run, delta t. So I found the slope between those 2 points. And that slope is my average velocity. That's always going to be true. If you have a position versus time graph like this, the average velocity is the slope between 2 points on that graph. All right, average speed is one that we will not actually use very much, but it's one that you have a sense of in everyday life, so I have to tell you the difference between it and average velocity. It's distance over time, not displacement. So, distance over delta t. It's so unimportant for us that I'm not even going to give distance a proper variable. So the big difference is velocity is a vector quantity and speed is a scalar. So again, it's that velocity has a direction, speed does not. But there's also another difference, and it's essentially the same difference as displacement versus distance. So I'm going to give an example to kind of illustrate this. Say we're taking a trip from A to B, could be 2 towns or whatever. And maybe it's like a mountainous area. So you got to take a pretty meandering path to get there. It's like a winding mountain road. Maybe that distance is 300 miles. But if you look on a map, you'll find that the actual separation of points A and B, if you drew a straight line between them, is only 100 miles. I think I sort of gave it away, but which of those is telling you about distance and which is telling you about displacement?
The 300 miles is your distance, and the 100 miles is your displacement.
Yep. And sometimes you'll hear the displacement as the crow flies. It is the direct path because a bird doesn't have to follow the road. It can fly straight from A to B. So this is my displacement. And technically, if it's a displacement, it's a vector quantity. I went, just judging from the picture, sort of southeast. I won't get into the, south of east, this many degrees, but somewhere southeast. All right, now say a road trip from A to B takes 5 hours. So what's your average speed?
60 miles per hour.
Yeah, because the distance was 300 miles, took 5 hours, 60 miles per hour. And this is what you would see on Google. If you're looking up, how do I get from here to Nashville or something, it'll say, well, it'll take about 5 hours, and that's assuming you're going an average speed of about 60, because you're mostly on highways. So average speed might actually be a better descriptor for a human being a lot of the time. It's what's useful to us. But average velocity is the one we're going to stick with, because if we shrink it down to much shorter times, it'll turn out to be the better quantity to worry about in terms of describing motion. But we won't really see that till we get to instantaneous stuff on the next page. But anyway, it would be 100 miles over 5 hours. So 20 miles per hour. It's lower just because the bird does not have to go nearly as far as we do, and so it doesn't have to fly as fast to cover it in that same amount of time. And again, strictly, I should pop in a direction. We see the distinction?
Yes, question.
Mhm.
I know you said it really doesn't matter about the average speed thingy, but the SI
Oh
units,
my
is there
goodness. I've been doing this
something
for
about
days. Like every class I've been missing that. Thank you. It is the same as average velocity, and that makes it confusing. In fact, all four of these speed quantities are measured in meters per second, and that makes it hard to tell sometimes which is which. I want you to also try this one, because it's kind of the same thing. I want you to find average velocity from this position time graph for these three different parts of a trip. So hopefully it'll be pretty fast, but just take a minute and try this one. Don't worry about what goes up here. I'll draw that in. Okay, do we have an answer for that first one?
200 meters per second.
Almost. You may have forgotten to divide by the
2
time.
meters per second.
Yes, yeah, so I think it's just that factor of 100 from the time, maybe. So it is 2 meters per second, except you're still missing something.
East.
It is east or positive. And again, I'm not going to continue harping on this. It's not going to count you off or stuff like this on exams unless I'm specifically asking for a direction. It's just to say, like, that positive has meaning. It's not just a placeholder to say this number is bigger than 0. Okay, so one way you could have found that is just found any two times for which they were in segment 1 of the trip. So maybe 400 seconds. And then at that point, they were at 800 meters east of their reference point. And then you could compare that to 200 seconds when they were about 400 meters east. And then all you're doing is finding the slope between those two times. So that is my delta t. And this is my delta x. And just from that, I can see it's going to be positive. It's a positive slope, an eastward slope. But I can do final minus initial. And that does come out to positive 2 meters per second. I can tell just by the slope being positive that the biker was moving to the east, because we called east the positive direction. All right, what about segment 2? It's easier.
It's 0 meters a second.
Yeah, because for any times, anywhere between the start and end of segment 2, I am always at positive 1200 meters east of my reference point. So my delta t could be this entire time span. My delta x is going to be 0 because I didn't go anywhere. So my final position was 1200. I should say positive 1200. If I'm going to catch you on it, I'm going to catch myself on it. And that's true between 1,000 or 600 seconds and 1,000 seconds, but it's true between any two times in segment 2. I will get 0. So the slope was 0. And in this case, I can conclude that they're stationary because they were always sitting exactly at 1,200 meters. And that's actually what these pictures up here, or these squares are for, is to watch me draw a horribly drawn bike. I'm sure everyone else's is better. I will be checking when we get back in person. It will be for a grade. He's going to the east. It won't because I'm failing currently. Here, I guess he's taking a break. That's what's happening for segment 2. And then what do you think is happening for segment 3?
He's going left?
Yeah. How can you tell without even having to calculate anything?
Negative.
Yeah. The slope is going to be negative. I can see that just by looking at it. So he is, in fact, going the other way now. But if we want to be specific, we just pick any two times and any two locations. So I'll say, all right, at 1,800 seconds, he's at about 400 meters again. So I'll compare this point to maybe where he is at 1,400 seconds. And it looks like he's at 800 meters again. So if I just find the slope between those 2 points, I will know his exact average velocity. Again, this is my delta t, and this is my delta x, and it's going to be negative this time. So it will be, he ended up at positive 400 meters. He started at positive 800, and the final time was 1800. The initial was 1400. So we get, looks like -1 meter per second. And I shouldn't be surprised that it's, for 1 negative, we already figured that out, that it's a negative slope. But for 2, it's a shallower slope than in segment 1, which we already found to be 2 meters per second. So this indicates that he is moving to the west. Because the slope was negative, he was moving west. Now, because of that thing I said about how east and west are actually up and down on these graphs, so this is towards the east, this is towards the west, it can be very confusing if you are not used to it yet. So one thing you can do, if you're fine with this, don't worry about this, but if the graphs are confusing, rotate them. Either on paper, redraw it, or in your head, rotate it. And what I mean by that is, I'll just take this whole graph and redraw it. And now position is the horizontal axis, and east and west are the directions they should be. And now you can pretty clearly see what's happening. I'm going east here. I'm not moving here because I'm not ending up more east or more west than I started. And then I'm heading back west. And you can do that for any of these graphs, if, again, you find the original graph confusing to think about. And this last thing is that the average velocity always has the same sign as the displacement. It's kind of telling you the same thing as displacement, but now it's also telling you the rate of motion, how quickly you got from A to B. But we have that issue I was talking about of, for instance, in this one, I could go somewhere and then come back to my starting point. And the average velocity would say, oh, you weren't moving. Even though I know I was. In this case, I went east and then back west. So what's the solution to that? If I want to be more accurate about my motion, how can I fix that problem?
Instant velocity?
Yeah, so instead of thinking about a whole 3 seconds, which that's a lot of time for something to happen, start thinking about much shorter times. What is my average velocity over 1/10 of a second, or 100th, or 1,000th of a second? Then I don't have enough time to turn around or do all these things that make my calculated motion, what the velocity says, disagree with what I know happened, my actual motion. So average velocity is not good at sudden changes in motion. And so we will start considering much shorter times to calculate this average velocity, and we'll call that the instantaneous. How fast and which way an object is moving right now. And now that could actually mean like some other time than the present moment. That's just to say at an instant. So in this particular flash of time, you take a screenshot of someone driving. Can you figure out how fast they're going at that instant you took that picture? It really is just calculating the average velocity, but over a much shorter time span, over a time span that's shrinking to 0. Or, if we remember what average velocity is, that's displacement over time. But what is this? We did have to do pretty rapid fire coverage of it, but let's go into our chapter 1 notes real fast. So I'm looking at the limiting case of a change in one quantity over a change in another as that denominator one goes to 0. We call that the derivative. So this is the derivative of position with respect to time, meaning little change in position per little change in time. That doesn't have to mean that the velocity is a tiny number, because this is a ratio of 2 numbers. Even if they're both tiny, you can get a large number out. But this is just the little step forward you take per each fraction of a second that passes. And that tells you something about your motion. It tells you about your instantaneous rate of motion. Speed, the instantaneous speed, is actually easy. It's just take the velocity and throw away the direction. Just worry about the size of it. So it is the magnitude, or again, that just means the number of that velocity. Sometimes written like absolute value of it. And in everyday life, this one may be more what you're used to. The instantaneous speed is what a speedometer measures. Whereas instantaneous velocity, you'll need both a speedometer and a compass. Something to tell you how fast and which way you're going. So if we come back to that example of a road trip between two towns, that's still 300 miles. This is still 100 miles. I found that the average speed was 60, and the average velocity was 20, maybe southeast. But that's describing the totality of a 5-hour-long trip. It's actually not saying a whole lot about the details of the trip. That is where I start to consider the instantaneous velocity. Instead of saying, well, over that first 5 hours, how did my position change? What about over the first 1/10 of a second? How did my position change? And in that case, I'm going to follow the actual route. I started at A and then ended up just a tiny bit further along. And that's what I'm calculating that average velocity with. And if I do that over a 1/10 or a 1,000th or a millionth of a second, eventually I get something descriptive of my motion right at that instant. And that would be my velocity right then. And I could calculate it at some other times and find that it's a little bit faster. Maybe this is where I'm going on a highway. I'm going 70, or if you're a Memphis driver, 90. Here, I may be passing through a sketchier area where there's rocks up on the cliff or something, so I'm going to drive a little more cautiously. So I'm going 20 miles per hour. And so my instantaneous velocity can be all sorts of different numbers. This might be, I'll just call it northeast. And then this will be maybe 20 miles per hour southeast. And it can be all over the place, as long as it averages out to about 20 miles per hour for the entire trip. Then the instantaneous speed is just the number. So it's pretty easy. It's just 20 right here, or 80 when I was here. Just throw out the direction bit. Does that make sense?
If you're going north or south, what is the sign?
What is the sign? So that's a good
Yes,
question.
the
I'm sort of cheating because really in this chapter we're focusing on 1D motion, in which case I'm only allowed to move east or west, or separately I could move only north or south. In these examples, I'm sort of looking at actual motion like north, south, east, west, any direction I want. And in that case, it turns out actually just using a positive or negative is not enough, because it could mean north, south, east, or west, depending on what I choose to call positive. So in the next chapter, we'll see the full details of this, and the answer turns out to be I either use 2 positives or 2 negatives, or a positive and a negative, something like that, to say both east and north. Does that make sense?
yes, thank you.
Yeah, so good catch on that. This is a 2D motion that I'm describing. It's just easier to picture than a 1D motion, even though kind of we're stuck talking about 1D motion as far as the quantities we're talking about at the moment. Okay, if we want to find that on a position time graph, well, that graph is now going to be curved because I'm covering different amounts of distance from one moment to the next. And so, to find the velocity on a curve, it's still that process of finding the slope, just like we were doing. But now this limit thing means I got to find the slope not between 2 different points, but the slope at a single point. Because the time between the 2 moments I'm capturing to calculate this slope is shrinking down to 0. And again, that's the definition of the derivative. So on my picture over here, if I want to find how fast I'm going at exactly 20 seconds, like if I glance down at my speedometer or my compass, what's it say right at this moment? One option I have to find that is start by calculating the slope between 2 points that are a little far away from each other. So say in this case about 5 seconds apart from each other. And I say, okay, that kind of gives me that slope, but it doesn't perfectly line up with the graph there. And so what I'll do is, now I'll try maybe just 2 seconds. What's the slope between those 2 points, the black point and the green point? And that lines up a little better with the curve, but still not quite. But that's this limiting process of looking at closer and closer points until eventually the second point lines up with the first. So it gets closer and closer and closer until I'm essentially calculating the slope between that point and itself. That's the one that actually touches the curve, is actually the slope of the curve at that instant. And that blue one is what we call the derivative of this graph at time 20 seconds. It is that tangent line, the line that is just grazing the curve at that point. And again, if you've taken calculus, this is hopefully familiar. If you are in it right now, you may not have talked about this yet, but you'll get there. So we're going to do some practice with that. We will need to know how to evaluate a couple derivatives, this power rule thing. For people who are in calculus right now, have you said the word derivative yet?
Like just barely.
Okay.
Just brought it up.
But I think y'all also take the engineering, I forget the name of the course, but the intro engineering course, and they just give you this really bad crash course in calculus, right?
Yes.
Okay, so you have heard of this concept, but probably they didn't teach it very well in that class. That's just what I've heard. So if this is not completely clear, that's fine. You can kind of meet with me in office hours or anything, and we'll clear this up. But also, you'll see it pretty soon in calculus. We've got several position time curves, and they're a little bit more complicated than previous ones. We're going to try and figure out things about the motion. I want to first do it visually, using these tools we've already developed of just looking at slopes and whether they're positive or negative and that kind of thing. And then we'll see that the math agrees with us. So we'll actually evaluate the derivative after the fact. So for this first one, what would you say about the velocity, the motion of this object?
It's positive.
It's positive, so they are moving to the east. What else would you say about it?
It's constant.
Constant. It's a constant slope, never changing. This is someone who is always moving east and always going at exactly some fixed speed. We'll see maybe it's 3 meters per second in these units, but maybe something like 10 miles per hour, just a constant value. So this is you coasting along a road. And I can tell that because I look at the slope, because it's the same thing as velocity. It is constant and positive, meaning to the east. Now I actually evaluate the derivative, because that gives me velocity. What is the derivative of 3t minus 2?
3.
3. And I might even throw in a positive. Wow. It's positive, and it's constant. So this is someone who's always going 3 meters per second, let's say, to the east. So that one's not super exciting. Neither is number 4. I'm going to jump to number 4 for a second. What's happening there?
It's stagnant.
Yep. The slope is 0. They are stationary. Because this position that they're at is never changing to a new position. But what's the derivative of a constant?
0.
Crazy. All right, now we'll get to the slightly harder ones. Tell me what's happening in 2.
It's moving west.
It is moving west. How can you tell that?
It's on the negative side of the graph.
It is on the negative side of the graph. I'm going to be a little bit more careful and say the slopes are negative because you could be on the negative side of the graph and moving east if you're going that way, right? So it's not only that you are towards the west, that's what being in the negative part of the graph means, but moving west is that the slope is negative. So the slopes here are all negative slopes. So that slope is negative. So they're moving to the west. What else would you say about it?
It's not constant.
It's not constant. What's happening to the slope?
It's accelerating westward.
Yeah, it's getting steeper and steeper. They are actually going faster and faster. Your brain may think because we're in the negative part of the graph, that means something about slowing down, but think about the actual numbers for these slopes. The number describing that slope, maybe it's -2 meters per second. But this one, this slope, it's steeper, so it might be a more negative number. And then an even more negative number. So they are actually speeding up while going westward. So it's becoming more negative. So in this case, that actually means speeding up. That is a little counterintuitive. But let's evaluate that derivative.
-4t.
-8t.
Yeah, so it's going to be -8 because we do bring down that exponent and then subtract 1. So it becomes a t instead of t squared. But we also, since we brought down a 2, that gets multiplied by the 4. We do end up with -8t. But look, that's a negative, meaning west. And then as time goes on, 8t becomes a larger and larger and larger number. So they're moving west, but going faster and faster. All right, now for number 3. What would you say about that slope?
It's decreasing.
It is decreasing, so if I sketch it in, I can see it's getting more and more shallow. So what would you say about that vehicle or whatever it is? What's it doing?
It's decreasing until it comes to a stop.
Yeah, so it's slowing down. And which way is it going?
It's basically going west.
Yeah, because the slopes are all negative. So the slope is negative and decreasing. They are slowing down. And so let's evaluate our derivative to see if that agrees. So for this one, remember that this is the same as 2 times t to the -2. That may be easier to work with for a derivative. What would it be?
-4t? No,
Almost.
never mind.
Okay, I see something for
2t.
almost. You're kind of going the integration route.
-4/t cubed.
Yes, there it is. So we take our exponent, we bring it down. So we multiply -2 by 2, that's -4, and we subtract 1. So now it's t to the -3. So this is going to be -4t to the -3, or that's -4/t cubed. If we look at this, there's a negative. They're going west. And as t gets bigger, what happens to this whole thing over here?
Becomes smaller.
Yeah, because they're slowing down. V is a negative number, but it's a number that gets smaller and smaller, closer to 0 as time goes on. This is someone coming to a stop. So, this is just to say that the math agrees with reality, agrees with the actual motion, and so our tools we've developed to describe motion are good tools. And this is where instantaneous velocity wins out over instantaneous speed, because not only does it tell us how fast we're going, but which way we're going. It adds that feature that speed does not have. All right, and so these questions are pretty easy now that we've done this. In which situation is the velocity, or in other words, the slope, constant?
The fourth one?
The fourth one, and
Oh, the first one.
yes, was that a cat or a human?
Yeah, that was my cat. I'm
Okay.
sorry.
It's like, because it almost sounded like it said 1, and I thought, did a baby just answer this? Okay, so 1 and 4. Because constant velocity just means constant slope, which means a straight line. And you may also notice, in that case, it doesn't actually matter whether we calculate the slope at a single point or the slope between 2 points. We'll get the same answer either way. That's saying that if something's moving at a constant speed in a constant direction, so constant velocity, the average and instantaneous velocities agree with each other. It doesn't matter whether you calculate how fast you're going over an instant or over an hour if your speed never changes. In that case, they will both agree. And then when is the velocity negative? So when is the slope negative?
In 2 and 3.
Yep. Negative v just means a negative slope. And so I would advise for anything like this, just sketch in, like draw the slopes at different points, and that may fool you less than what your brain says about that this is in the negative part of the graph.
The EST or CST that you wrote for A is what is that?
Oh,
I
constant.
might have missed that.
That's my abbreviation
Okay.
for constant. And now what we can do is if we plot those slopes over time, we calculate it for every point on a position time graph, we can make a new graph, a velocity time graph. And in fact, that's what I was getting at on this page in the first chapter notes. I'm calculating a derivative. I'm taking slopes of this graph to draw a new graph. And this will be my velocity time graph. So these things are actually starting to have a point rather than just, I know this page is a mess, but there is rhyme and reason to it. So let's do that. I'm going to find slopes for this position time graph to say something about the speed of this thing. And just to ground it a little bit, this is someone getting in an elevator, going up the elevator, and getting out on the top floor. So they get in, they go up, and then they get out. That's the motion that I'm plotting here. And now this actually is plotting their height as a function of time. So, well, yeah, let's just start with that. Where are they not moving?
Initially and finally,
Yeah. So how can you tell?
it's when the elevator's not moving, and when they're not in the elevator.
But like,
Oh, and the slope is 0 at those
yes,
points.
yep. So the slope is 0 here. That's saying the velocity is 0 at those times. And now I'm just taking that and deciding to plot the velocity itself on a new graph. Okay? Where is the velocity constant? They're moving at a steady pace.
From about 1 to 8 seconds.
I would say not quite from 1 to 8, because look at the slopes right there. You see how they get steeper?
Mhm.
But you're close. You have the right idea. It's just maybe skip that first little bit. So from
Maybe
go ahead.
3-ish to 7.
Yeah, 3 to 7, or I think we could stretch it to 8, because like if I look at this, that looks pretty constant, the slopes. I'm going to say about 3 to 8, and I'm going to say that because I know that's the right answer. So between here and here, it looks like that curve has a constant slope. And that means they're moving at a steady pace. I can also actually find what that slope is, find that velocity. Because since it's a constant, the average and instantaneous velocities are the same the whole time. So I can just find a slope between any 2 points. I'll pick between there and here. So that looks to me like about 4 meters and 24 meters. So if I calculate this slope, should be final minus initial over final time minus initial time. 20 over 5 is 4, but it's a positive 4. And in this case, since I'm using up and down motion, that positive refers to upward motion. It's an elevator, not a east to west type motion here. And so I can put that on my graph. Between 3 and 8 seconds, I am moving at 4 meters per second in the positive direction. All right. Now, what about between 1 and 3? What am I doing there?
Increasing sorry, you go.
Sorry, I was gonna say you're accelerating and then decelerating.
Yeah, so here the slope is getting steeper, and that does mean I am speeding up because I had to get from 0 meters per second to 4 meters per second somehow. That's what's happening in between. Now, do I know that it's happening at this steady pace where I'm gaining the same amount of speed per second? No, I don't know that just from looking at this graph. I need an actual function like I have up here and take a derivative, or I just need to kind of parse this data a little better, do some numerical differentiation. I'm just saying connect the dots. That's all I'm concerned with for this graph. So I'm speeding up here. Okay, and then you did already say that between 8 and 9 seconds, that slope is getting shallower because we got to get back to 0 by the end of this. That does mean slowing down, which I don't know why I just said speeding down here. I don't mean like a speeding ticket. Speeding up. There we go. So I'm getting back down to 0 meters per second in this last bit. I am slowing down. Effectively, what I just did is I graphically took a derivative. I found slopes at every point and made a new graph out of those slopes. So that is like from chapter 1, this procedure of taking a graph, plotting its slopes on a new graph, and that new graph plots the derivative of the original one. Now, for acceleration, I like that you said acceleration and deceleration, because in physics, we don't do that. We just call any change in velocity an acceleration. So it could be speeding up. That's what we're used to in everyday life as acceleration. But slowing down to a physicist is acceleration. And the most confusing, just turning. Even if I'm always going 20 miles per hour, if I'm turning, I'm accelerating. Why? How could that be?
You're still moving when you're turning.
I am, but acceleration is not just about moving. It's about my motion changing. So velocity both has a size, how fast you're going, and a direction. And for turning, the direction you're going is always changing. That's a change in your velocity. It's not as obvious a change as speeding up or slowing down, but it is a change. And so we still consider it an acceleration. So my way to know what's an acceleration is if it feels like it. That's an acceleration. Because think about when you do know that something's changing when you're in a car and when you don't feel like anything is happening. Where do you feel like you're just relaxed and not being pushed into your seat or pushed into the door or anything? What kind of motion makes that happen?
When you're not moving
When you're not moving is one option for sure. There is another time where it
or going
feels
straight?
going straight at a steady speed. So if you're on the interstate and you're going 70, it actually doesn't feel that scary because you're just on this smooth ride, at least if there's no potholes and things like that. That is the only thing that is not an acceleration. So I'll say rest. That was the first one you said. Or coasting, meaning a steady speed in a straight line, are not accelerations. Everything else you can possibly do in your car is. If you're on a bumpy road, you're going to feel some up and down accelerations, or side to side from your suspension if you're hitting bumps left and right. If you're speeding up, you feel like you're pressed back into your seat. Something has changed about your motion and you feel it. If you're slowing down, you may lurch forward into your steering wheel. Again, something has changed. And if you're turning, you feel like you're pressed into one of the doors. Something feels different. That's how you know you're accelerating. All right, and we're going to go through the same procedure of saying, well, how violent is that change? How quickly is my velocity changing? And that's what average acceleration measures for us. Change in velocity over time. So it's, I'll write delta V. Change in velocity over the time it took, but change is again final minus initial. And what would its units be?
Meters per second squared.
Yes. So it really is meters per second, the units of velocity per second. And that honestly is easier to think about because it's saying my velocity changed by this many meters per second per each second that passed. For instance, 3 meters per second is saying I was going 20, a second later 23, second after that 26, 29, something like that. Meters per second squared sort of masks that. It's a shorthand. It's just that you may find yourself someday saying, what is a second squared? And it's because it isn't anything. It's just a shorthand for meters per second that passes. So average acceleration, it's there to measure how sudden, or I would even describe it as how violent the change in velocity is. If you have to slam on your brakes, that will feel like a violent change in velocity, a very sudden one. Or if you have to floor it to get on the interstate, that will feel like a pretty violent change in velocity. Or if you have to take a really fast turn, pretty violent change. Right, and we'll do some math with this. So we've got a plane. It eventually reaches 260 kilometers per hour after 29 seconds. So slightly different units, but we'll stick with them for this. What is the average acceleration? Let's figure out what numbers need to go in here. So what's the final velocity?
260 kilometers
Mm-hmm.
an hour.
Yep, in the positive direction. What was the initial velocity?
0?
Yeah, it's not stated, but I mean, it's a plane going down a runway, so we can assume. And that sometimes it will say like starts from rest or something like that, but sometimes it's just, you're a human being. You've seen a plane take off. It starts from rest. And the final time is 29 seconds. We could call the initial time 0 seconds if we wanted to, or just consider this to be your delta t, your elapsed time. Either is going to give the same answer. So the units come out a little funky. It comes out to, it'll be positive 9 kilometers per hour per second. But I actually like that because it makes this clearer what the acceleration is telling you. What does this say to you?
It increases by 9 kilometers per hour every second.
Yes, exactly. So the velocity, I'll say, changes by 9 kilometers per hour each second. If we had called it 9 kilometers per hour second, that would be correct unit-wise, but would make no sense physically. So we start from 0 kilometers per hour. After 1 second has passed, we are expecting this plane to be going about 9 kilometers per hour. Due to this positive 9 kilometer per hour per second acceleration that occurs. And after 2 seconds have passed, we're expecting it to be going how fast?
18 kilometers per hour.
Yep. Now this does assume it is actually a constant acceleration. That would mean like you've got your foot kind of in the same spot on the accelerator. You're not pressing harder and harder or anything, but you are gaining the same amount of speed per second. All right, and now we'll look at this other case. So starting from 9 seconds, I guess that's just how long it took for them to cross the finish line. They deploy a parachute to slow down from 28 meters per second to 13. And they do that over a span of 3 seconds, between 9 and 12 seconds. So what's the average acceleration here? Let's see, the final velocity was 13. The initial is 28. And then final time was 12, initial was 9. That does come out to -5 meters per second, which we could abbreviate as meters per second squared. But again, I actually like this version a little better because it's saying the velocity changes by 5 meters per second each second. And in this case, it's actually that if this thing starts at 28 meters per second in the positive direction, but the acceleration is 5 meters per second in the negative direction, how fast will this thing be going after 1 second has passed? So I'm starting at 28, but I'm taking off 5 meters per second per each second that passes.
23 meters per second?
It'll be 23. I'm just stripping off 5 meters per second at a time. So after another second has passed, how fast is it going?
18 meters per second.
Yep.
Per second.
Just 18 meters per second, because I'm describing how fast it's going. This extra per second is saying I'm taking off that much per each second that passes. So minus 5 meters per second per each 1 second that we advance in time. And if I waited 1 more second, I would now be going 13 because it's been 3 full seconds. I'm down to this new final velocity. So I know I'm out of time. I just want to write one more thing from these. I know looking at this, it's tempting to say that negative means slowing down and positive means speeding up for acceleration. But that is unfortunately not the case, at least not always. What is true is that if my initial velocity and the acceleration have the same sign, that means speeding up. So both positive or both negative. Think about that. If I were going negative 260 kilometers per hour, which just means going to the west, for instance, then a negative acceleration would actually make that a larger number in absolute value. It would take me farther away from 0. So it's that the same sign for each means the object speeds up. If they have opposite signs, that's your acceleration disagreeing with your velocity. That's what slowing down means. And that's the last thing I'll write. Okay, so same sign means speeding up, opposite sign means slowing down. There is no special rules specifically about positive or negative acceleration. You have to know about velocity as well to talk about speeding up or slowing down.